Buenos dias, Jesus, Dr. Cruz.
Okay, my microphone was
Muted.
off. Uh, Now, can you hear me?
Yes.
Yes, okay.
Buenos, buenos,
How are you,
buenos
Professor?
dias. Muy bien, gracias.
You are now in Virginia?
Pardon?
Are you in Virginia? Is your
I'm in South
central?
Carolina, but next week I'm
North Carolina.
South Carolina, but I'm coming down next week,
Okay.
a week from Thursday.
Okay. Good morning, Professor Pesh.
Yeah, I see.
And welcome
Good
to
morning.
San German.
Morning, and I see Dr. Page and Dr. Yarman, I guess, from Turkey. Uh, Acquaintance for a number of years now. Very interesting.
Hello. Okay.
Okay, I guess Brian's not here though yet. I guess hasn't come yet. Bill, do you hear? Or Dr. Page?
Yes, I'm here. No problem. Just
So,
getting a bit organized here on my
okay, good.
desktop.
Hello, Garrett, and dear all, hello. This is. Do you hear my voice? Hello.
Oh, hello, hello. Nice
Welcome.
to meet you. Mhm.
Yeah, I just started reading the interesting email you sent me, uh, Dr. Yarman.
Dear Garrett, indeed, it was a hashed email, but I'm glad you had the time to read it, dear Garrett.
Well, I haven't read it all. It's quite long, but it's
Yes,
interesting.
indeed.
I'll read it later on.
Okay.
Okay, well, I guess we can wait a few more minutes just to check whether Brian is going to come. I know there were at least two other people, Dr. Sobczyk, that you mentioned
Yeah, I'm
were
not really
invited.
sure. I think that Dr. Yarman's father might not be able to make it, but I'm not sure about Dr. Havel either. He might not make it either. Everybody's very busy.
Yes, well, that is the difficulty of interacting by something like Zoom, where everybody has to be connected at the same time. And,
I just got back
though,
from a doctor's appointment. I'm glad I could take care of it uh, in time. That I could make the appointment and also do get back in time here for the Zoom. I'm sorry I missed it last week. I completely threw me off with these the way the system works with these links.
did you, by the way, Dr. Sobczyk, did you receive another link today for this
Yes,
meeting?
I did.
Hmm.
In fact, that's
Yeah,
how I got it. I clicked on that link.
it's a new email that you received today.
Yes.
Hmm. I'm I'm confused by that. I don't quite know how that email gets generated. It's not sent directly by me.
Well, it
Uh,
looks like it comes from the calendar, Zoom
yes, it,
calendar.
it must be the way the Google Calendar interacts with your system, like through. Uh, I know I've had other people explained to me that it reacts very differently if you're on a Macintosh or something like that. And then you then you see a completely different way of being invited. But in any case, as long as a link isn't actually necessary, as long as you know both the meeting number and the passcode. So that's the.
I picked that up. I sent that to Dr. Yardman. The old, I guess it worked all right. The old one.
I had to go through a few links to get to you, dear Garret.
Yeah, it's a little confusing.
The technology has advanced too rapidly for us all.
Well, I think
Yes.
you're probably the most caught up of everybody, being the younger generation.
Yeah, a little bit, yes.
Right. Well, I guess we can sort of begin. Today, I think our main objective was to have a presentation by Dr. Sobczyk, I guess an update on the work that you've been telling us about now for a few meetings. Last meeting, we discussed category theory and its sort of relevance with in terms of defining Grassmann algebras, and some aspects of what Dr. Cruz discussed last week or last meeting suggested a possible approach to understanding the difference between global and local duality, but in a much more formal way, or maybe I should say more categorical way of describing this difference. That was only a tentative sort of conclusion that Dr. Cruz and myself sort of.
Hey, I think I can. The last 2 weeks have really been very important for my own trying to understand what's going on. And what I've come across is what's called Finsler geometry. And I think it's extremely close to Finsler geometry. So that's one of the main topics that I'll be talking about today is Finsler geometry, what it is, and how I think that what it has to do with this, what I call local and global. Well, I think it will clarify.
Okay, that's interesting, yes, because from my understanding, my once run-in with Finsler geometry has to do with in terms of differential geometry, where it's viewed as a kind of generalization of Riemann geometry.
Exactly.
In particular, where the metric may be degenerate.
Well, it can have cross terms, dx, x. Yeah, so that's exactly what I'll be mentioning that and pointing out a paper by Chern, a very important paper, and a book by him.
Yes. All right. Yes, that sounds very interesting.
I guess we can get started. I'll share it. I hope I can. I fixed things myself.
Only a comment. I sent to you about 2 weeks ago a copy of the one draft of the with the ideas that we have been discussed before. And
Yes.
I only organize these ideas in this draft, and I think that now we can read it in a better way. By the way, Professor Sobczyk, can you send a copy to Professor Yardman?
Yeah, I sent a copy.
Maybe later, maybe.
I'll send a paper. No, I haven't sent a paper yet. I will send you the paper, the slides I'm talking about today, I'll send them out right afterwards.
Okay.
But there is
Sent
this,
them out, yeah.
the summary that you just sent, Jesus, that was only 10 minutes ago, right? That's
I haven't,
that's a new email from Dr. Cruz
oh,
about
okay.
10 minutes ago.
I sent to you in the mail that you sent
Or-
say the
but actually,
participation of Professor
I have
Jarman.
a totally new title today, and everything's new. So it'll, yeah, what I'm going to
Okay.
talk about today is different a little bit. I didn't know about the Finsler geometry with the previous talk I gave over a month ago, I guess it was.
Yeah. Yeah, this what Dr. Cruz is talking about is a kind of summary of the techniques in category theory that are relevant for defining duality.
Oh, okay.
That's a new document, and I think it is. I just took a quick look at it, and it's
Okay, I haven't
definitely,
looked at it yet. I haven't looked at that yet then.
yeah. Okay.
Okay, so I'm going to
All
share.
right.
Okay, let's see whether everything's here. Okay, so I should be able to open this up. Can you see the screen with it? See if I can make it bigger here. you
Yes,
see
Garret. Yes, it's a full screen now. Yes.
Okay. I'll leave it just a little bit because I have another that I want to show you also. So let me just start by reading my new title, Null Vectors, Local and Global Duality, Null Vector Manifolds, and Finsler Geometry. So null vectors are metric-free and define oriented rays on the Minkowski-Einstein light cone in special relativity and in higher dimensional null cones. The concepts of a local and global duality on a set of null vectors makes possible a new classification scheme of real and complex Clifford geometric algebras. It is shown that Finsler geometry is equivalent to null vector geometry, a null vector manifold. So I'll explain exactly what those things mean then as we go along. Okay, I've renamed this picture I've shown you before null vector tree because, as Dr. Page pointed out, it really wasn't directly related to category theory. So I'm going to, let's see if I can so I'm going to talk about this more. The whole, it really is a picture which summarizes the whole, my whole talk. But so, okay, I'm going to introduce what's called this universal algebra of null vectors. And I'm going to show how it's related to Grossman algebras of what I call correlated Grossman algebras, two Grossman algebras, G of A and G of B. These are A and B are sets of n null vectors. So a null vector is a vector which has square 0, but okay. So I have to tell you what correlated null vectors means and how that's related to geometric algebra. Now, local, that's called global duality. Local duality is this other situation which is very important, which seems to be not recognized at all. But I'm going to show you how that's related to Finsler geometry. So what I'm going to do now is I want to shrink this screen down a little bit, and I want to show you this other paper here of Chern's to explain what Finsler geometry is a little, and then I'll come back to my paper here. So let's see if I can do that. Let's see here. Okay, I don't want this screen here. Let's see, where can I get this other one here? I'm afraid to do anything really. Okay, I have another paper that's on.
Dear Gareth, if you double click the title bar, it should minimize.
If I double click what?
The title bar, the screen should minimize.
Okay, but let's
The
see.
title bar is where the name of the document resides.
Okay, so I've got to get back to the document then. How do I get back there?
We see the document on the screen, June 19,
okay.
2024.
Oh, okay, let's see. Trying to get back here. Oh, let's see here. Okay, okay, there it is. Okay, now I want to move this. Okay, this is what I wanted to show you now for a little bit. Okay, can you see this? Finsler geometry is just Riemann geometry without...
No. Dear Gareth, we do not see the new paper you see on your screen. You have to represent it.
Oh, okay. So I need to stop and then share again?
Yes.
Okay, let me do that then. Okay, I'm going to share again now. And I should be able to get back. Okay, and now I want this to open. Okay, can you see it now?
Yes, that's right.
Okay, thank you, Dr. Yarman. Okay, so let's talk a little bit about this, and I'll go back to my talk then. Okay, so here it is. Also gives some history. 1854, Riemann introduced a metric structure in a general space defined on element of R. Okay, so here it is. ds equals a point. That's a point x1 to xn. That's a point on the manifold. And then x dx1 up to dxn. That's the differentials. And the metric is defined by what's called f squared, and it's gij is a metric tensor. And then you have dxi dxj. So usually a metric tensor only has quadratic dxi squared, and but that's what distinguishes general Finsler geometry from ordinary Euclidean geometry. Now, okay, so his report, I will send you all a copy of this paper as well. It's on the internet. This is a notices article, September 1996 by Chern, a very well-known American Chinese mathematician. So it appeared in the notices in this year, 1996. So his report is divided into the following sections: connections and the equivalence problem. What he's referring to here is one or two Finsler geometries equivalent. So I will try to address that issue in my talk as well. Second variation of arc length and comparison theorems. Okay, so I'll address some of those issues. Harmonic theory, very important. The relationship of harmonic theory to Finsler geometry, and also what David Hestides and I developed in our book, the idea of a vector manifold. And that's exactly what I did in my PhD thesis, talked about vector manifolds, started laying down the basic ideas there. So I will show you the references later on that. Okay, complex Finsler geometry. Well, I hope to tell you what that is in terms of null vector geometry, as I call it, and that's related, of course, to this what I call local duality. This is very interesting. The Gauss-Bonnet formula is generalized in Finsler's geometry done by Chern. And the interesting thing about that is in my book with Professor Hestides, my PhD thesis advisor, we have a chapter on the Gauss-Bonnet formula. worked out in terms of what we call vector manifolds, which is idea that was central to my thesis back in 1971 when I got my PhD. Okay, so let me see, is there anything else I want to say here? Well, okay, so he introduces the usual language. So f of x1 to xn, y1 to yn are coordinates. These are the coordinates of the point, and this corresponds to the coordinates of the differentials. So anyway, I think that, well, okay, so I'll let you look at this. So I'm going to get out of this now. I guess I can just shut it. You say
You
if I
have to close the presentation and restart a new presentation to get back, dear Garret.
okay, I need to stop right again. Stop and go back to the other one. Or maybe I could just X this one out now. Maybe I better not do that. Let's see if I can. Okay, can you see this other one now still?
No, you have to close this presentation and
Okay, I
represent.
have to shut it. Thank you. Okay, let me close. I'm going to stop sharing. Okay, and I'm going to share again to get back to the other thing. Okay, so okay,
Registered.
Yes, we can see it.
okay, now I can make this into a full screen. Okay, is that all right?
Yes.
Okay, thank you. So let's go on then. Okay, I already read the introduction, so I won't read that again, but you can get some better idea from looking at the other paper what we're talking about. Well, okay, so the main thing again is this local duality, which I'll talk about now, and global duality. So let's give a couple of definitions, which you're familiar with if you've been to previous seminars. Okay, so universal algebra of null vectors. This is this is what I think is missing, and it should be covered. It's very basic concept in terms of which you can define matrices, linear algebra, and all these ideas. Now Finsler geometry as well falls under the same null vector perspective. So what is a null vector? A null vector, so this universal algebra of null vectors, what is that? Well, that's the set of all these null vectors made into an algebra. Well, you get the algebra by taking Grossman algebras of null vectors. Say, well, here, that's what I have. A null vector V over a field F is an oriented direction or array with the property that V squared is equal to 0. So it's not the usual. Usual vector has length and direction, but a null vector or array only is built on a null vector. There's no metric involved. It's just a null vector. And it represents a oriented direction or array. You can think about that as being on the null cone in special relativity. And that's how this Minkowski metric or Lorentz metric becomes involved. Okay, null vectors V are added and multiplied together according to the same rules of matrix algebras over a field. Okay, a 2 to the n Grossman algebra, that's this notation right here, is contained in the universal algebra of null vectors, is generated by a set of n anti-commuting null vectors v1 to vn, also contained all in this universal. Notice I say 1 because they're vectors. Vectors are different than bivectors, trivectors, and so on. That's the graded structure of a Grossman algebra that's involved here. Okay, so I denote then the geometric algebra 0, 0, n is just a Grossman algebra generated by a set of n null vectors. And here I'm just introducing notation. All the vectors, those are the generators of the algebra, of the Grossman algebra. We haven't introduced geometric or Clifford algebra yet, just Grossman algebras. These are the vectors. These are all the subspaces of the grading structure of the Grossman algebra. Okay, and they're all contained in this null vector algebra over a field, which in this case is just the field of real numbers. most important is the field of real numbers and the field of complex numbers. But we can also consider it over finite fields, where we can talk about these other ideas I was mentioning. The projective plane, the finite projective plane that we've talked about. Okay, so again, we have the graded structure. I'm just introducing notation. In the Grossman algebra, which I'm denoting the same with the symbol G of K vectors, they're K null vectors. They're all null direction, no metrics involved at this point. Oriented directions of the n things taken K at a time basis of K null vectors in the Grossman algebra. Well, I give references here. Like I say, I will send this paper along with the, okay, simple example, n equal to 3, complex Grossman algebra of null blades over the complex numbers. So that's important. Okay, so again, the notation. This is called the geometric algebra of null vectors. And over the complex numbers, it's the G3 of C. That's just a Grossman algebra spanned by V1, V2, V3, which all have square zero. They're null vectors. We also have bivectors, V12, V13, and so on. Vij is Vi, Vj, and that's the same. That's where the wedge product is now. Notice that so I'm using the Grossman product now becomes, I'm going to write it as equivalent just to the wedge product. And of course, it satisfies the anti-commutativity property equal to minus Bj Vi. Okay, and the pseudoscalar trivector null vector, again, subscripts V1, V2, it just means the product of these Grossman null vectors. And now if we take the complex null vector, V1 plus Vi times V2, and square that, well, we find that it also has magnitude 0. So we'll go more into that, why that's the, well, okay, let me just keep going. Okay, so now let's talk about definitions of global and local duality in the universal algebra. Okay, now this is important. This first line is important. A single null vector, C0, in the set of all null vectors and generated by vectors is identified with a chosen oriented ray in any direction. We're just looking at what's generated by a single null vector. And in this case, we're mostly interested in the complex numbers, but we can consider the single null vectors over the complex numbers. Okay, and now I'm going to introduce some metric structure. Well, you can see how the metric gets involved. So we say two null vectors, V1 and V2 have square 0 in the set, the universal algebra of null vectors over any field, finite field, or the very important, the finite fields, which I've talked about before, but I won't talk about here. I'm only interested real and complex numbers here. Okay, so now you see, now I'm introducing an inner product in terms of the null vectors. Okay, so we say that V1, two null vectors in this universal algebra are plus or minus conjugate if V1 dot V2 defined to equal to the symmetric part. The anti-symmetric part is taken up by the null Grossman algebra that we've talked about. It's independent of the symmetric part. So I say they're conjugate if these two null vectors in the universal algebra of null vectors is equal to plus or minus 1, okay, either one. Now, it follows that V1 and V2 are mutually annihilating idempotents that partition plus or minus 1 respectively. Okay, note that the conjugate null vectors V1, V2 in this universal algebra of null vectors are not anti-commutative Grossman null vectors, because in this case, we've hijacked the symmetric part, because these null vectors now are what we're calling plus or minus conjugate, okay? A set, okay, so let's look at, so a set V1 through Vn of null vectors is said to be correlated if for each one let I not equal to j less than or equal to n, that 2 vi dot vj is equal to this thing is not equal to 0. They're correlated. They're pairwise conjugate. Well, they're said to be locally dual if they are pairwise conjugate. So that means that 2 vi dot vj is equal to vi vj plus vj vi is equal to 1 minus the delta function. So, of course, delta ij is equal to 0 if I is equal to j. Well, if I is not equal to j, okay, so you can see the inner product is always equal to 1 for pairwise conjugate null vectors. Okay, and now you see, now we take two Grossman algebras, one generated by a set of n null vectors, which I call an, and a second Grossman algebra generated by a set of b1 up to bn null vectors. They're said to be compatible if for all I1 to n, 2ai dot bi is equal to ai bi plus bi ai is not equal to 0, and globally dual, that's the other definition of if the inner product, when j is equal to I, then you see ai dot bj is equal to 1. Okay, that contrasts with this other case of pairwise conjugate, locally dual pairwise conjugate. That's equal to 1 minus delta ij. So that's a different concept than local and global duality is a different concept. But defined on this null vectors in this universal algebra. Okay.
Sobczyk, question. Here, definition of local duality is saying that is the same that the definition of conjugate vectors.
Exactly. I'm going to talk about that a little more as we go along still. So. Yeah, that's right. Contravariant and covariant vectors are exactly identified with.
I don't say here covariant and covariant, but
I haven't mentioned that here, but that's exactly what we're talking. So you can think about A1 to AN as being contravariant null vectors, whereas the B1 to BN are covariant null vectors. So I'm going to talk more about that. So I don't want to.
Dear Garret, is that what you mean by correlated between the two sets of geometries?
Well, yes. Compatibility. That's right. Globally dual. We say these are globally dual because A1 dot B1 is 1, A2 dot B, well, 1/2. They're all equal to 1/2. AI dot BJ is equal to 1/2 for the inner product, but expressed as symmetric part, you have A1 B1 plus B1 A1 is equal to 1. That's the compatibility relationship.
SWBR.
Okay, but now you're going to see how I'm going to define the Clifford geometric algebra in terms of these two Grossman algebras of null vectors, okay? And here it is. Also, I give references, so I will send you these papers when I'm finished. So EI is just AI plus BI. So these are unit vectors. These are actually vectors. The usual Euclidean vector, E1, E2 are just Euclidean vectors. And the Fi are anti-Euclidean vectors. These are orthonormal vectors I'm defining. E1 dot E2 is 0. F1 dot F2 is equal to, these vectors here are square minus 1, okay? They're anti-commutative. Well, these properties are all easily followed, and I just give a reference to it so you can look at that. But here it is. Now, let's give the simplest example. Simplest example defines the Clifford algebra, sometimes called the mother algebra, but I'm not going to go into that. So G11 is equal to 2 orthogonal vectors, one which has square plus 1, E has square plus 1, F has square minus 1. This is what I call the spectral basis. So we take the product of the A's and the B's. We have BA, that's an idempotent if you look at it. Then we have A, it's like a column vector times a row vector of these elements. So if you multiply this column vector, you get BA times BA, and that's an idempotent, so it squares to 1. Then BAB is equal to B. And then you have ABA is equal to A, and AB is also, these are mutually annihilating item. Well, that's right. So if you multiply BA times AB, you get BA squared, B squared, that's 0. Okay, so BA plus AB is equal to 1. BA minus AB is equal to it's equal to E. Okay, yeah, okay, there it is. Okay, now position vector is the usual, well, this is a Lorentz position vector, x1e plus y1f. E is equal to A plus B, F is equal to A minus B, and they satisfy this relationship. E squared is equal to 1, equal to minus F squared, EF equals minus FE. Okay, they're anti-commutative, they're all orthonormal. We call that the standard basis of the geometric algebra G11. Okay, now the corresponding coordinate matrix of that element is what I call G11, G12, G21, G22. And you can write G in terms of, express it entirely in terms of these null vectors A and B by using this formula here. And notice that okay, you have this too. You have G11BA, that corresponds to this algebra. Okay, G21 corresponds to the element down here. G12 corresponds to B, and G22 here. So you see a direct relationship between the matrix of it, the coordinate matrix algebra, which is also the generators of the geometric algebra G11. And here you have it. The matrix of the null vector A is just 0, 0, 1, 0. Matrix of the element B is 0, 1, 0, 0. Okay. Okay, basic theorems. A locally dual Grossman algebra, G is generated by a set of n plus 1 vectors in the universal algebra of null vectors, which I denote by C1 dot 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 up to Cn plus 1. I probably should make this 0. Maybe instead of, there are advantages of using C0, C1 up to Cn, but okay, so the slide is with up to, so we have n plus 1 null vectors from the universal set of null vectors. Okay, gives the geometric algebra G1 at 1. And now I'm defining the standard basis. So what is this algebra? This is the algebra of anti-commuting vector, which has square plus 1, and n anti-commuting orthogonal vectors, which have square minus 1. And now you can see, to get the relationship between the standard basis and this set of null vectors, which are locally dual, is simply by this notation I'm introducing. Cn means the sum of the first k of them, okay? And alpha k is this constant. You'll see, get more insight into what that is by minus the square root of 2 over k times k minus 1. Okay, E1 is C1 plus C2, like we saw before in the easiest case. F1 is C1 minus C2. Fk is equal to this constant here I defined, minus the square root of 2 over this, okay? And, okay, and there you have it. Fk is equal to alpha k times the sum of all of them, using this notation, times that, okay? Okay, the simplest example, always good to look at the simplest examples. The geometric algebra consisting of one vector which has square plus 1 and two vectors which have square minus 1. Okay, and that's what we call the real number system extended to include these two vectors, E1 and F1, which are anti-commutative over the complex numbers. Okay. And I let J, okay, now J in this case, okay, actually I'm identifying J with the pseudoscalar element. That's the trivector null vector. If you square this out, you'll find that J squared is equal to -1. Actually, my notation, I might have called that I instead because I'm using J for, that's the thing. You could either, okay, I don't want to go into that detail. But again, the spectral base is exactly what we wrote down before. Remember, I had the A's and the B's, B1, A1, A1, B2. Okay, anyway, it's the same thing in this case. Well, again, the same rules. E1 is equal to C1 plus C2. But now in this case, notice that we have 3 of these null vectors. C3 minus C1 plus C2. The coordinate matrix in this case, okay, notice that C1 and C2 are exactly the same as with the A and the B, but now C3 is given by J and minus J. Okay, so that's interesting. I'll talk more about, well, if you square this matrix, you'll find it's equal to 0, okay? It's a null vector. Remember, C1 dot C2 is equal to 1/2. C1 dot C3 is equal to 1/2. They're all equal to 1 as before, as we define the rules. Okay, the symmetry group was very interesting when expressed in terms of G1n. And what we do, okay, it's generated by C1 up to Cn plus 1 null vectors, which have square 0. And for this element, Sn plus 1 is a product of all these things, C1 up to Ci, up to Ci plus 1, and so on, up to Cn plus 1. And now we define the symmetric group. Okay, this is the permutation of 2 elements, Ij. Okay, notice what it does. So when I apply the permutation of 2 elements, Ij, it permutes, when I multiply, okay, it just interchanges the Ci, and these are in order, 1 up to I plus 1 up to, these are all in order, but when I multiply by this permutation of I and J, it anti-commutes these 2. And now the theorem tells you exactly how that works. To get that, all you have to do, so the permutation, taking I into J and J into I, operating on this element here, the product of all these nilpotents, remember these are all nilpotent vectors here, is -1 to the n plus 1, Ci minus Cj, Sn plus 1, Ci minus Cj. I'm missing a parentheses here. Okay, G12, okay, I'm proving some basic, this theorem is not difficult to prove, but I'm not going to go over that. It's easy though, you can follow it in the, okay, now, so again, we're at this null vector tree, which I wanted to emphasize. So here it is big. Okay, so again, what is the structure? That's the set N, the universal algebra of null vectors generated by a set of N null vectors, V1 up to Vn, if you remember. So it's a set of all these null vectors, and then you multiply, it generates an algebra under the usual rules of matrix multiplication. So it's completely compatible with matrix multiplication. Okay, and now you have the Grossman algebra is generated by N null vectors, A1 up to AN. Okay, that's a Grossman algebra we talked. G of B these are the contravariant, if you want to call them that, null vectors A, the covariant null vector elements B. But now you have this extra thing, which I call local duality. And that's what which I now recognize it makes what I'm calling the null vector manifold equivalent to
Finsler. Finsler geometry.
No, Finsler's geometry, exactly. Finsler manifold, that's exactly right. Okay, so there we have it again, the picture, the same picture, which I've discussed a little bit. So with global duality, notice that the star operation takes the algebra, the null vector, the contravariant null vectors A1 up to AN into B. Okay, and you take the double dual, that's why I call it global duality, you get back to A again. But local duality, okay, now you can see why I'm using the term local duality. It, of course, generates the geometric algebra G1n. That's when the antisymmetric part is equal, the symmetric part is equal to -1, and the symmetric part is equal to +1. That's the other geometric algebra. This consists of n vectors which have square -1 and one vector with positive square, whereas this one is one vector, one vector with positive square and n vectors with minus square, orthonormal vectors. Okay, and now you can see, take any pair of these null vectors, and I'm using C0 to Cn, okay? So any pair of them, distinct pairs, they're locally dual to each other. Namely, in this algebra here, C star I is equal to -Cj, and on the other hand, in this geometric algebra, C star I is equal to Cj. That's local duality here, the relationships. The double relationship gets back again, and you put the two together, you get what I call the quadratic algebra of G1n. Okay, so I'm sure that's a little confusing, but that's just notation right now. Okay, fundamental relationship between global and local and global duality. Relationship between Clifford algebras is always confusing, nonetheless extremely important. Starting with the concept of null vector and local geometry, all multivector linear algebras and representation theory can be based on these two concepts. So the traditional approach, as you can see, I hope, corresponds to contravariant vectors and covariant vectors, as we're talking about, well, coordinate-wise, okay? I mean, you look at the coordinates, and that's related to covectors and tensor analysis and category theory. Well, that's what Dr. Cruz and Dr. Page are experts at, category theory, which I think is now very close. I'm being able to tie it closer together now with this idea of Finsler geometry being intimately involved with these ideas. Most interesting relationships between global and local duality is summarized in the following sequence of isomorphic real and complex geometric algebras. We have, okay, notice I'm taking this over the complex numbers now. So that's the same thing as the geometric algebra over the real numbers of 2n plus 1 null vectors, okay? Or notice this, that's where the local duality comes in. This geometric algebra is either related to 2n1, that's the covariant part, and this is the contravariant part, but they're all, as complex algebras, they're all isomorphic to 1, 2n minus 1. But this is, okay, so in the standard basis, Gn n plus 1 is exactly E1 to En, F1 to Fn, and then we have an additional one which has square minus 1, which I call Fn plus 1. Okay, I try to explain why the geometric algebra consisting of 2n Euclidean vectors over the complex numbers is exactly the same thing as this geometric algebra. Well, okay, you can see 2n is the same, 2n 0 over the complex numbers is the same thing as a real geometric algebra n plus 1 over the real numbers, okay? So this complex numbers now is given a geometric interpretation. So this is, again, as far as geometric interpretation, I squared is equal to -1 is the ordinary complex number, so it doesn't have any direct geometric interpretation. All the elements in the algebra have a geometric interpretation. So that's what I'm saying here. The pseudoscalar element, I, is the product of all of these, E1 up to En, F1 up to N plus 1. That's in the center of this geometric algebra. That's what makes this relationship true. However, there's a crucial difference in the meaning of these two isomorphic but different geometric algebras. One of these geometric algebras is real, so that all its multivectors have an exact geometric interpretation, whereas the other, the meaning of the imaginary multivectors, is hypothetical. This has important theoretical implications in the interpretation of the Pauli algebra. Okay, I give references there. Consider now the split isomorphism. This is the interesting thing. That's where the local duality is involved. Notice that Gn n plus 1r, it's isomorphic to 2n1 over the real numbers in some cases, or if it's not isomorphic to that, it's isomorphic to this geometric algebra. And that follows from the basic fact that 2n minus 1 or 1 minus 2n is either isomorphic, is either equal to 3 mod 8 or 7 mod 8. That capital explains why it's either or relationship that we have here. But again, that's a fact from classification of geometric algebras, which I give references to. Split isomorphism tells us that the real geometric algebra is alternatively isomorphic to G2n1R or this one respectively. They are also alternatively isomorphic to the corresponding matrix algebras over the complex numbers. So this is where the correspondence between any Clifford algebra and matrix algebras is very well understood. But in my way of looking at things, our way of looking at things, a matrix algebra is just the coordinate matrices of geometric numbers, of null vectors in this case, generated by null vectors in the universal algebra. So we're a step above matrix algebra. Clifford algebra is isomorphic. There's always matrix equivalence of Clifford algebras to matrix, its corresponding matrix algebra over the real or complex numbers or pairs of such algebras. Well, here, example. G12 is isomorphic to the matrix, complex matrix algebra over 2 by 2 matrices over the complex numbers. I is equal to the square root of -1. But G21 is isomorphic to 2 copies of the matrix algebra, real matrix algebra. That means an ordered pair where each ordered pair is only multiplied by just the usual product of, it preserves the ordered pair. So that's the difference here. Okay, notice, but in this case, if I go from 1,2 to 1,4, then a pair of quaternion algebras, 2 by 2 matrix algebras of quaternions is isomorphic to G14, but G41 is in the complex matrix algebra. So again, okay. Because signature is unimportant when considering geometric algebras over complex numbers, we have 2n minus 1, comma 1 over the complex numbers, I squared equal to I is equal to square root of -1, is the same thing as the geometric algebra 2n minus 1, 1, because 2n minus 1 plus 1 is the same thing as 2n. And then 2nc, again, that's the same as 2n. And then this one, 1 comma 2n minus 1 over c, they're all isomorphic in terms of their matrix algebras. Every geometric algebra GPQ, that's any signature, has unique geometric structure when it's expressed in terms of the fundamental null vector generators of the universal null vector algebras, all in the universal algebra of null vectors. Whether in terms of the mother geometric algebras, which I'm calling these algebras GNN over a field, can be finite or otherwise, or the real father geometric algebras, 1, 2n minus 1 over f. In both the cases, they're corresponding isomorphic coordinate matrices matrix representations serve as powerful computational tools. So that gives you a way of, if you try to multiplying in this basis of null vectors, it can be very complicated, but that's why the isomorphisms, the corresponding matrix algebras, is important as far as computational wise in both either the local or global geometric algebras. Okay, I'll give an example here. G12, again, generated by one vector which has square +1, two vectors which have square -1, and they're all anti-commutative. I, in this case, is equal to E1, F1, F2. And notice what I'm doing here. Remember, that's in the center of this algebra here. You see, that's different than J, which I'm saying J is a usual square root of -1, whereas I, in this case, is in the center of 1, 2. Okay, so it commutes with the whole, it acts like J does, really. Okay, but notice what I'm doing here. Because it's in the center, I can say E1, F1, F2 is the same thing as E1, I, F1 times minus I, F2. And that gives you E1 times E2 times E3. Because you see, I'm saying where E2 I'm defining equal to I, F1, you see I times F1, if you square that, you get +1 because it changes the signature. But notice I'm calling this now E2 equal to E1 times F2. So E2 in this geometric algebra is a bivector. Well, you see, we're reinterpreting the elements IF1 and minus IF2 as being in the Euclidean space generated by three orthonormal vectors E1, E2, and E3. Okay, by identifying the bivectors E1, F2, E1, F1, and G2, 1, 2 as anti-commuting basis vectors, we have almost magically turned the geometric algebra 1, 2 into the isomorphic geometric algebra of Euclidean space, G3, 0. Well, here's the isomorphism, G1, 2, isomorphic to G3, 0, which is the usual polymatrix algebra of polyvectors, important in quantum mechanics, and they're all isomorphic to 2x2 complex matrices then. But you see, this gives geometric interpretations to all the elements where the G3, 0 is generated by imaginary, the complex 2x2 matrices over imaginary numbers.
Dear Garret, sorry, does this mean that you can map any kind of algebra to an Euclidean or Cartesian backdrop?
That's right. You can map it into a corresponding matrix algebras.
So you have to read my email regarding that today. Okay.
Pardon?
You have to read my email to you regarding that topic today, indeed.
Okay, I'm going to send you this paper along with the references and everything that you need to
I have the paper. I looked at it.
Oh, that's right. I sent you that already.
SWB audio count.
Okay. Okay, so this observation is not without important physical consequences. The coordinate matrices of Euclidean vectors make up the polymatrices of quantum mechanics. Let J equal to this, equal to J times this. Then you have G21R, and we have the same algebras now, except you can see the case of G03 is now imaginary because remember we're interpreting that as whereas this algebra is a real algebra now, you see? That's the idea where it flips back and forth between this is a real geometric algebra, considering these as the elements of the algebra, okay? So we have the scalar 1, then we have E1, F1, JF2. That's what changes the signature of this vector into square +1. And then we have this bivector E1, F1, J, and so on and so on. And this algebra now, okay, this is the interesting thing here. Well, you can see these are vectors now, with geometric interpretations. And in this algebra, we have these are the vectors here, Jf1, F2, Jf this. So they're different geometric interpretations. In each of these cases, we must interpret J not equal to I. See, I now is a pseudoscalar element in that geometric algebra 1, 2, whereas J is the ordinary square root of -1, okay? Otherwise, the pseudoscalar element would not be well defined, okay?
This also plagues Einstein with his pseudo tensor.
SWB audio capture not registered.
Okay. Okay, so go for, I'm sure the others could hear Professor Yarman's question, but we'll go back to it later. So for G21, note that, okay, now these elements S1 plus S minus are partition unity. These are mutually annihilating idempodes which partition unity, and they're mutually annihilating just says that S plus S minus equal to 0. Let's see, do I define them here? I guess I don't define them. Maybe I do. Well, anyway, so G21 is isomorphic to the algebra of two matrix algebras which are commuting with each other. Well, they're ordered pairs. You can think about it as being a 4x4 matrix algebra with 2x2 matrices down the diagonal. So you can see that corresponds to a pair of 2x2 real matrices. And this corresponds to a pair of quaternion matrices. Okay, let us now consider the fifth line. Okay, so this is I'm trying to sketch out the classification of geometric algebras using this, using the Clifford algebras G1, N, instead of the usual covariant and contravariant classification on global duality, which is global duality. This is based on local duality of geometric algebras, which involves no metric. And if you look at Finsler geometry, that's what they emphasize. And Chern talks about, yeah, it can be very confusing to mix up contravariant and covariant. In fact, for these contravariant and covariant, for this local duality, we say contravariant and covariant don't exist. They reduce to the same concept. That's the interesting thing about global duality. So that's an important point, which becomes clear if you look at the Finsler geometry that it corresponds to.
Sorry, dear Garret, do I understand that contravariant and covariant mean the same thing under this setup?
On local duality is the same thing as that's right. What did I say? What was your question again?
So under this setup, contravariance is the same thing as covariance in this local
duality. That's right. In local duality, contravariance and covariance are exactly the same concept. That's the difference between local and global duality. Global duality, contravariant vectors correspond to the A1 to AN, and covariant vectors correspond to B1 to Bn. But in local duality, Ci and Cj for distinct pairs are locally dual to each other. That's why I call it local duality. Each pair in that basis of C1 to Cn plus 1 are locally dual to each other. I hope that finally makes the distinction between local and global duality.
Excuse me, Professor, I like if you could discuss more about the meaning of local and global duality, starting from the generators sets that you have here and in the page before, the page 10. You are these generators. Then how is those two concepts of duality present in each of this?
I'm not quite sure.
Can I just
Yeah,
make,
you're a
I
little
just
bit
want to
garbled.
make a,
I don't quite understand
yeah,
everything.
can I want to just make a comment. I think Dr. Cruz, I think your microphone setting is perhaps too loud.
Okay.
You seem rather broken up when you're talking.
Yeah, I had difficult understanding the question completely too.
Maybe you can listen before now.
Now it's better. Now it's
Now it's
better.
better, yes.
Thanks.
Yes. Okay.
My question was that starting from these sets, from these generated sets for the different algebras, how is expressed here the concept of global and local duality?
Okay, yeah, that's exactly the point.
Okay.
Global duality is expressed in terms of what I'm calling contravariant and covariant null vectors. Okay, so a contravariant vector as a null vector corresponds to A1, A2, the Grossman algebra, A1, A2 up to AN. The covariant vectors correspond to the B's, B1, B2 up to Bn. In the Finsler algebra case, they're all put in the same algebra. And that's exactly what we're doing here. We're putting the A's and the B's into one algebra. Now, the local duality is generated, well, you can see we have n plus 1 null vectors, C1, C2 up to Cn plus 1, and they're all locally dual to each other. And that simply means that each pair of them satisfy that local duality relationship. C1 times C2
this
C2
makes
times C1 is equal to 1.
So this makes this kind of geometry characteristically equivalent to Finsler geometry.
Exactly. That's what I'm trying to show, that it's the equivalent to Finsler geometry. And that's exactly what Chern is doing in his paper. And he says it's confusing. He mixes that notation up because he doesn't have the concept of local duality. He's using the traditional concept of what I call global duality. And that's where you're identifying contravariant vectors and covariant vectors as the usual concept of covectors and vectors and covectors being different. I'm going to give you another example of that. Maybe go on and I'll give you an example where you can see that more clearly.
But still you must have a problem here, in as much as even in Finsler geometry, we need to know the difference between a vector and a form, a one form, right? So that when you were showing the introduction to Finsler geometry by Chern, you included both x and dx.
Yes.
And so x and dx are of different character. They are not in the same algebra.
I understand what you're saying, and maybe you're right. Maybe this actually goes beyond Finsler geometry, because that's right. So maybe it's sufficient to use what I'm calling global duality to represent Finsler geometry, and we don't need. But okay, so that would be all right, but that would make this even more general than Finsler geometry. But let me go on then, and I will maybe we'll clarify some of the ideas as I go on. Okay, so let's. Okay, so this is an interesting example here. Okay, I've talked about that now already. Oh no. So okay, let's look at how G31, this is a classification of geometric algebras, the geometric algebra generated by three vectors which have plus square, one vectors which have minus square, why that is isomorphic to the geometric algebra G22. And that follows from this relationship. So G31 by definition is generated by 3 Euclidean vectors, E1 squared equal to E2 squared equal to 3 squared is equal to plus 1, F1 squared is equal to minus 1. All of these vectors anti-commute. But notice that I can write that as G22. Why is that G22? Well, because look, we can consider the same algebra generated by F1. So this is the geometric algebra generated by E1 comma E2 and F1 comma F2. But now you can see this algebra here on this side. You can think about that as F1, that has square minus 1. That's one of these vectors. E1, 2, 3, well, that's a trivector in this other algebra. That behaves like these are all anti-commuting. And if you multiply them together, it's just a reinterpretation of what a vector in this algebra is compared to what it is in this other algebra right here. So here we
Garret, does this mean that the Finsler geometry is reducible to Euclidean geometry?
Well, yes. Well, that's part of the question that Dr. Page is asking, whether there might be something. But let me go on. I do have one last section I want to talk about, and I'll try to get into that issue more clearly of what's going on. Then we can try to think about that maybe a little bit. Okay, but so the interesting thing here I'm trying to make is that this geometric algebra is the same as this geometric algebra, where we're taking elements from this one and reinterpreting them as being these are all vectors. In this other, what's a trivector and bivectors correspond to pure vectors in G31, which I think is extremely interesting, which you don't have when you look upon that with just what's called, well, these vectors here, of course, covectors and contravariant vectors and covariant vectors in this geometric algebra. But on this side here, it's something quite different. That's where the local duality is involved. So that we'd have to study that more in terms of the Finsler geometry if there's something corresponding to that. So, okay. But notice if I multiply these 4 vectors together, what's vectors here, I have F1 times, well, that's a trivector in this geometric algebra, but it's behaving as a vector over here. That's a different interpretation. We have F1, E1, that's this bivector here. Well, these are all vectors. I'm considering that these generate the same, that's why the isomorphism between these two algebras is we have plus, plus, minus, minus. And here we have 4 elements in this geometric algebra, which we're just reinterpreting these elements as being vector. The grading is different. And if you multiply these things together, you get minus 2. Well, that's all right. If we're talking about the quaternion algebra, instead, we know that ij times k, the quaternions, is equal to minus 1. That does not generate the full geometric algebra. But this relationship is minus E2. So that properly generates this geometric algebra 3-1 as we claim.
This is fascinating, dear Garret.
Okay, so let's see. We now identify the isomorphisms, G13. Okay, well, I'm not going to go into these things, but the same decomposition, you have mutually annihilating idempotents, and that's how you can separate these off into pairs to get matrices of 2x2 quaternions. A pair of matrices, well, this is just a single matrix with quaternion entries. Single matrix, but quaternion entry, those are these geometric algebras, 1, 3, and G04. On the other hand, if you look at G40 and G13, that's the same isomorphic. Well, again, that's the same as isomorphic, the same matrix algebra, 2x2 matrices over the quaternions, okay? So these 3 are all isomorphic by picking out the right elements. Well, actually, you can see what they are, but I'm not gonna, I don't have, okay. Okay, now this is where I want to tie it together with Finsler geometry in a more detailed way, and we can maybe more address Dr. Page's question, which maybe is not completely answered in this, what I'm going to tell you right now. Okay, so in his 1996 paper, Finsler geometry is just Riemannian geometry without quadratic restriction. Chern gives an introduction to Finsler geometry. With co-authors, they wrote this book, number 18, which was written in 2001, I think it was. So I have the references. Other researchers have explored the topic in terms of Kaluza-Klein structures. Well, they're related to Clifford algebras. In fact, just another name for Clifford algebras, or geometric algebras. Now, the interesting thing here is that Heifer, or I don't know how, this is a young Dutch theoretical physicist who just got his PhD in the Netherlands. This is what really introduced me to Finsler geometry. I saw that he got some international publicity, and that clued me off to Finsler geometry. Gee whiz, must be closely related to this stuff. So I looked up. That's what I did 2 weeks ago. I've been thinking about Finsler geometry for the last 2 weeks because I saw his thesis and I looked through it briefly. But again, I referenced that because it did motivate my whole looking into Finsler geometry and trying to understand its relationship to local and global duality to Finsler geometry. Okay, in 2.15.13, the authors explored the concept of vector manifolds. So that's my book with Hestenes. I'm referencing my thesis here, and one other. Anyway, it's in the references. Okay, vector manifolds. So again, that was what concerned me in developing my PhD thesis. And then in my book with Hestenes, this is where we prove, where actually Hestenes found the proof of the Gauss-Bonnet theorem, but which is also generalized in the Finsler geometry, which, well, would carry over now, since I'm claiming here that that's equivalent to Finsler geometry, but maybe in light of Dr. Page's question, maybe it isn't completely equivalent. I'm not sure. So, but let me talk about it, what I do know about it. Generalize the concept of vector manifolds to 2 kinds of Finsler geometry: globally dual Finsler manifolds and locally dual Finsler manifolds, appropriately defined by global and local null vector manifolds. Okay, so Bill is questioning, Dr. Page is questioning the local duality aspect. Okay, well, let's look at those ideas a little more closely. In a vector manifold, partial derivatives playing the role of contravariant vectors are replaced by directional derivatives, and covariant vectors are replaced by their dual null vector equivalents. In global duality, replace contravariant and covariant vectors by null vectors. Okay, this is global duality, AI and BJ. So that's what I've explained already. So partial XI corresponds to AI. And now that corresponds, considering this to be the gradient operator, call it the Finsler geometry gradient operator, a directional derivative, AI dot the Finsler gradient operator. So it's turning into well, here that's what they identify as contravariant vectors. Well, I'm saying no. Well, geometrically, as a vector space, you can consider it to be a vector manifold where AI are null vectors which generate the same direction as what in Finsler geometry is a coordinate vector. Okay, and this corresponds to the contravariant vectors. But notice I'm taking the gradient operator of a scalar, okay? So that's the difference between partial xi and partial yi. In one case, it's the directional derivative, Finsler derivative. In the other case, well, I'm calling it the null vector manifold derivative now, you see. But I think
the second one, the second one is partial Vj, not Vi, Yj, not Yi.
No, YJ. That's right. That's oh, in your paper, I think I corrected that mistake. It should be partial J. No, that's right. This should be partial Y, partial J. I made a mistake. That should be a Y, not a J. Not that should be a Y here, not an X. Okay, I don't want to mix the two spaces together. Okay, that's where it can become. If you look at Chern's paper, you can see this problem comes up and he ignores it. He says it's simpler to mix the two together. Well, that's exactly what's possible with this vector manifolds that we introduced back. Well, the book was published in 1982. My thesis was published in 81. So you can see it's still not, mathematics community still has not recognized really the concept of a vector manifold. Now, there is some references to it, but I won't go into that here. Okay, in addition, okay, so again, that's the global duality relationship. AI.bj is the symmetric part of the contravariant null vectors, and the compatible or globally dual covariant vectors, bi. And okay, so it's 1/2 the delta symbol. When I is equal to j, it's 1/2. Not equal to j, they're anti-commutative. You can see that's what I'm calling global duality. Guarantees that AI is isomorphic to the matrix algebra 2 to the n over the real numbers. Local delta is a different story. Okay, so this is related to Dr. Page's question. And I think it's valid. I don't completely understand it myself. But you can see if you look at Chern's work, it's not clear exactly either, to tell you the truth. He says he's hoping the reader won't be confused. Well, that's why when I was a student, I developed this concept of a vector manifold because I was confused by fiber bundles and all this terminology that's necessary to develop the usual approach using contravariant and covariant vectors. So that's what's interesting. Here I'm coming now, I'm trying to introduce what I'm calling a locally dual null vector algebra. Okay. A null vector manifold, locally dual null vector manifold. But I agree that there's more work to be done. Let's see if I can look at it. So partial xi corresponds to ci. That corresponds to partial ci gradient f of x. Notice here I keep x.
Not
and
registered.
okay, this addresses Dr. Page's question. If this isn't true, then I am wrong. But I think that I still believe it's true. But again, I refer you to Finsler geometry and Chern's papers and Chern's book. But this is a point that needs. So I'm claiming that you can do the same thing. The dimension of this space is n plus 1, whereas the covectors and dual vectors is 2n. So the dimensions is much less. And if this is true, then it would simplify ideas about Finsler geometry, which Chern has gone. Actually, the reference, it's a huge reference out there, which like I say, I've really only studied it the last couple of weeks, which I'm glad that.
So is Finsler geometry a special case here in the locally dual scenario?
Well, I think that it is, but I can't really establish that rigorously. Let me just put it that way. But I refer you to Finsler geometry to try to help me understand. This point is, like I say, it's not completely clear how that works, but so you can call it a conjecture if you like. It's my conjecture that it is equivalent, but I have to say it's only a conjecture at best.
I have a question about the scalar that you introduce. I don't. You have a scalar phi there. So what is its
You
relationship?
mean, well, that's the inner product of these null vectors. Remember, that's a null vector gradient, so that's not equivalent to the usual gradient because, well, as you know, that's actually clear in Finsler geometry. Well, I'm claiming that, so it's clear to me that Finsler geometry is equivalent to at least some Finsler geometries are equivalent to the, well, he actually compares it to Riemannian geometry. So the global duality is, Finsler manifolds are not the same thing as Riemannian 2n dimensions, okay? So Finsler geometry is more than just global duality. And my conjecture is that with local duality, you get all other Finsler geometry as null vector manifolds. So that's my conjecture. I should make that.
But I do understand, I think, when you write contravariant vectors there in terms of this operator. So we have this differential operator, and we can associate the differential operator with this vector.
Exactly.
C sub I. That's very conventional.
Okay, and that's just Riemannian geometry, and that's why.
But the second one,
Finsler geometry goes beyond that. So okay.
No, but I don't understand the second part. Like in what's. In fact, I don't understand at all what's going on.
Let me go. I can maybe
that
clarify a
second
little bit
phrase.
about that. Look at this then. So what I'm saying then is that the tangent manifold or tangent space is equivalent to the cotangent space for locally dual Finsler manifolds, okay? And I'm trying to pin it down in terms of the Hessian, okay? So F squared is called a Hessian, but again, I refer you to my references here to clarify these, but that's what part of my conjecture then. I'm saying that the tangent bundle, or that would be the contravariant tangent bundle, is equivalent to the covariant tangent covectors, okay? And here I'm actually expressing in terms of the Hessian. So this is what we would want to examine in the future to clarify these ideas with more simple examples and so on. In this case, the metric is defined by the XY Hessians, Gij equal to 2 Ci dot Cj is equal to this, and I claim that that's equivalent. So the dimension now is n plus 1. Okay,
but dear Garret, you have to explain to us what these Hessians represent.
Okay, what is a Hessian? A Hessian takes the coordinates and multiplies it, forms a matrix xi, yj, x1, xi, yj. The coordinate vectors, puts it in a matrix where the Gij element is xi times yj. That's called a Hessian.
Is it a scalar or something else?
It's a scalar. Well, it's functions. It's just they're polynomials in xi, the coordinates xi and yj, xi and yi. Okay, so you can see when in this case j can equal to I. That's the diagonal of that matrix yi xi. But I'm saying that actually in this case xi is equal to yi and xj is equal to yj. But this is a diagonal matrix with the squares down the diagonal. That's the Riemannian geometry part of it. And the other ones, the xi, xj non-diagonal amounts of the Hessian, that's exactly what formed by the Hessians. Now, if you look at this, you take partial derivatives with respect to xi and xj. I claim that will generate these matrices I wrote down with ci, cj as a matrix. I don't have it written down here, but remember I've written it. Some of my other talks, I had C1, C2, C1 times C1 is 0. That's just the diagonal matrix then. For C0 times C0 is, anyway, I can't go too much more into detail of that, but that, I call it a conjecture. I think that's what I should make this into, a conjecture, because of the questions you've asked. And I haven't provided the details here to really firm it up rigorously, but I believe it is possible. And I still believe that local duality does, that the idea of a Pfinsler geometry is equivalent to the idea of what I'm calling a null vector manifold. The null vector manifold.
Do we understand that the global duality and the local duality encompasses altogether all kinds of Pfinsler geometries?
Exactly, that's what I believe. And that's what I believe this is showing, but I haven't produced the details. I need to produce a simple example where you can get the Pfinsler geometry in the local geometry case, which is just that, well, actually, that's just the pre-Riemannian geometry. That's Riemannian geometry, but it's when you add these other terms that you get you put the two together, you get the global. Pfinsler geometry, period.
And eventually all of this is reducible to Euclidean Cartesian coordinate systems.
Exactly.
Very fascinating.
Okay, let's see. Okay, so I say that TM, okay, what are we talking about here? Globally dual Pfinsler geometry is a pair. Okay, I'm trying to put it in terms of Pfinsler geometry, the Hessian of these coordinate X's and Y's, okay? Where the tangent bundle TM and the cotangent bundle is spanned by the sets A1. So I'm vectorizing it with the geometric algebra G, N, comma, N, okay? And you can see, okay, TM is spanned by the contravariant null vectors as the directional partial derivatives by dotting these null vectors into the Pfinsler gradient operator. That's a vector operator in the algebra GNN, if you want to look at it that way. Now, the contravariant Pfinsler manifold is spanned by the B1 to Bn. Okay, those are the off-diagonal terms, okay? Those are the xi, y. In the Hessian, that corresponds to x1, y1, x2, y2. Those are polynomials then, and that's called the Hessian. And by taking partial derivatives of that, you generate these vectors a1 to an. And notice this is as a scalar function. Okay, that's the relationship between how you represent the gradient, the Pfinsler gradient operator in terms of the null vectors a1 to an and b1 to bn. So that's the
SWB audio capture not registered.
Okay.
So the covariant scenario is interchangeable with the contravariant scenario.
That's right. This is the usual case that's dealt with in vector manifolds, but in the Pfinsler geometry case, that's right. We're putting the contravariant vectors and the covariant vectors into the same geometric algebra generated by GNN. Now the locally dual case, well, that's okay. Well, let's see, where do I talk about that? Well, that's where there's no distinction, you see. In the local duality case, we identify the tangent manifold with the cotangent manifold. And that's possible with the geometric algebra G1N. That's where the local duality takes place. But again, I'll leave that as a conjecture to be worked on. Well, and maybe my next talk in 3 weeks' time, I can try to work out a simple example to show that is indeed the case with the Pfinslerian point of view. But anyway, okay, then the references. Well, this is with Timothy Howell's work, with Heron's formula, which is interesting. It is closely related to these ideas, actually. And you've seen some of my earlier work by that. Okay, this is a book with David Hestenes where we talk about the Gauss-Bonnet theorem using the idea of a vector manifold, which is what I put down the first ideas in my dissertation back in 1971. Space-time algebra, well, that's Hestenes' famous book, Gordon and Breach. That also I studied in detail when I was working on my thesis under Dr. Hestenes' direction. Lunesto's book, Clifford Algebras and Spinors, Geometric Algebras of Light Cone Projective Geometry, that's published now in this conference paper, which is very related to these ideas of contravariant vectors and covariant vectors in the Finsler geometry, really. Geometric algebra compatible null vectors, advanced computational. Okay, that's the same thing where this other paper is published too. Where is that? Oh dear. Let's see here. Oh, light cone. Yeah, this light cone projective geometry is published in exactly the same place as oh, where is it now? Well, anyway. Oh, right here. Yeah, actually, these two go together, really. So in the same book here, Geometric Algebra Compatible Null Vectors, it's published in the same book. That's part of this conference. And that took place in, well, it's published in 2023. All right. Okay, these are preprints that have been published in either ResearchGate or in HAL. It's a French site, Global Local Duality. So these are basically preprints of unpublished work, but preprints that are published at these locations. Matrix Gateway, well, that is published. I'm the publisher of that using Amazon.com, which is useful for understanding of this idea of, the spectral basis and all these ideas. I developed and I classify geometric algebras in terms of this terminology as well, in this Matrix Gateway to Geometric Algebra. Conformal mappings, well, that was a paper I published in the AMS notices, and I thought that would help at least get vector manifolds recognized, but still it's not really fully accepted in the mathematical community. I hope that with this conjecture relationship to Finsler geometry, that maybe that will finally get geometric algebras, the importance of geometric algebras in theoretical mathematics. I think there's many interesting ideas, as you will get from looking at Finsler geometry. I think it might be related to the Riemann, the famous, what is it? Riemann.
The Riemann conjecture.
Yeah, exactly. About the all the zeros appear on the half line at 1/2. You can see 1/2 is extremely important in all of these. It's also important in quantum mechanics. And anyway, I would love that somebody would look into that. Students, I don't have. Well, maybe Dr. Yarman is young. Maybe he can prove the Riemannian conjecture. We can work on that together.
Inshallah. Dear Garret, do we have the chance to ask you a few more questions now?
Okay. So this is, again, I just give the references. So this is his book that you'll have. I'm going to send you these references so we don't have to spend more time on that. So yeah, sure.
Okay. So can I ask whether this would immediately translate to the standard model where certain quantum fields are conjectured, including the use of Grassmann numbers?
Okay, unfortunately, I don't think others hear your question. They say,
Okay, one more time. How does this translate to the standard model of particle physics, where certain quantum fields are described by Grassmann numbers?
well, it corresponds exactly. You just have to you can frame it all in terms of these vector manifold concepts. I might just mention that this Cambridge group of Lazenby, Doran, this Cambridge group, they've done very much work, and they have their own general relativity theory in terms of flat manifolds using the idea of a vector manifold. We hope that would get accepted even in the physics community, theoretical physics community, but it still is not completely. But that's a strong Cambridge University group that has been working on geometric algebra for many years now. So
okay, thank you.
Okay, so I'm not sure that the others can hear Dr. Yarman's question. They say he hasn't been approved, his audio. I don't know how to approve that. Can you hear Dr. Yarman's questions, Dr. Page?
I have no problem.
Cruz? Oh, okay. So I guess it's all right then. Okay. Any other questions?
Professor Garret, I have many questions, but because there are several points that are I don't get to understand because there is not a standard definition of duality here. Okay, you are using covariant and contravariant vectors, but I
call them contravariant and covariant null vectors to make it closer to
null vectors. But I can not find the definition of H in terms of the standard names that we used to use in generally in mathematics. For example, when you use the directional derivative for representing contravariant vectors, I understand this, but I don't understand how covariant vectors are defined in terms of directional derivatives.
Okay, actually, that's not difficult to explain. I can go back. Maybe I can go back to that slide if we have time still. Let's see where. Let's see. What do I want to go back to here?
Here, for
okay, maybe right here. Yes. So here you have partial xi. That's a contravariant vector, right?
Yes.
The usual terminology. That corresponds to a directional derivative ai dot what I'm calling the Finsler geometry gradient.
Yes, I understand that, but when you use covariant.
Okay, here it is. Here it is. You see? So I could write down an expression for the contravariant. So as a vector operator, I would need to add a line here. So this, what I'm calling Finsler gradient operator, can be represented as Bj times the directional derivative partial j. So it's Bj times partial xi. You see, because this thing is a vector as well. So I take this vector, I put this vector Bi in front of this one here, and that defines the vector derivative. So again, in my book with Hestenes, we developed those ideas, as well as in my thesis, when I was developing the idea of a vector manifold, which is still not widely accepted in the mathematics community, which is accepted more in the physics community, but still not generally recognized either. So, but anyway, that's where the idea comes from. You see, this is a vector gradient, whereas in the usual dual contravariant covector language, this is a vector, a contravariant vector, and well, it corresponds to the gradient of a scalar field. So that corresponds to the dual to AI, that's Bj. And if you look at AI dot Bj is equal to delta Ij. That's exactly like the usual definition of a covector and a
Okay, maybe here is my problem, because I understand that the gradient of a scalar field is a contravariant quantity and not a covariant quantity. Then this is the problem that I find here, because if we want to speak about covariant and contravariant, we need evaluation like is in the next line. And when we use evaluation, the place of A and B, okay, in not commutative algebra, are different.
yes.
Here, because one is covariant and the other one is contravariant. And then in this way, we can get evaluation. Then I think that when you put
Okay, so
tree
you're okay with this definition here. Partial xi is this, a directional derivative, but you're not okay with this other one. But you see,
yes.
That's how I'm embedding this into the same vector algebra. Maybe that's the geometric algebra GNN. So I'm putting contravariant vectors and covariant vectors by this trick here. It's a trick, but again, it's a different, that's not a directional derivative is not the same thing as a gradient operator of a scalar. Now, in Euclidean geometry, in an orthonormal system, then of course the gradient of the components is exactly the same. But so actually, maybe what you're saying is that in Finsler geometry, that it's not properly defined. Maybe that's why people have never accepted the idea of a vector manifold, because whereas I see this as a natural relationship, maybe I've been talking about Finsler geometry all the time. So maybe
Dear Garret, can you explain your trick in a little bit more detail, please?
Okay, well, again, so this part of the trick is understood, right? Okay, I wish I could, yeah. So
that's okay, certainly.
Yeah, I don't think I
It's the
can write
second
on it.
part.
Yeah, okay. So this part's fine. Okay, now this part. If you're looking at coordinates, then the Bj would be upper index. That'd correspond to Yj upper. Okay, so if I take partial x, partial Yj.
That x wasn't supposed to be there, you said before? You didn't want to mix up the spaces?
Okay, now the Hessian of this thing is, remember, x1, xi, xj, the matrix of x times the coordinates, xi, x1, y1, x2, y2, and so on, x2, y1. Those are all polynomials in the coordinates. The coordinates of this thing are x1 up to xn. The coordinates of this one are y1 up to yn. But of course, really, I'm thinking about Finsler geometry now, because that's exactly what they do in Finsler geometry. And that's where the Hessian comes in.
But
so
still,
maybe with your problem with this thing,
total confusion here. This is totally confusing. Like what is, okay, even if we replace x with y, what is the meaning of that derivative? It's no longer an operator, I guess. I mean,
well, what does it mean when you say they're a covector is dual to a contravariant vector is dual to is a covector. You say that if you take the partial derivative of the covector where the indices aren't equal, it's equal to 0, right? Well, that's like this relationship here. AI dot BJ is delta IJ. So I not equal to
that's
J.
that had nothing to do with that. The line above in the second, where you say and in that entire expression, none of that makes sense to me at all. I mean, I don't see what you're trying to write. I mean,
Well, like I say, maybe this should be rephrased totally in terms of Finsler geometry, because if you look at that paper by Chern, he will even say that mixing these indices together, the xi with the yj, can be extremely confusing, but he does it all the time because
here
of this relationship. This is the reason why I believe he does it in Finsler geometry, this bottom relationship, which you don't understand the connection, but that's, like I say, maybe it should all be
nothing wrong with that line. The last line I accept, right? And the first part of the line above I accept.
Why not the second part?
I don't understand it at all. It doesn't even make logical sense to me.
That partial x is written wrongly, Garret remarked half an hour ago. Didn't you get it?
Well, I did make what I wrote as a x should have been a y, but what I wrote previously.
Okay.
But that's in global duality. In local duality, then there's no distinction made. But that I'm clearly talking about geometry that goes beyond Riemannian geometry. But here, but that's the thing. In Finsler geometry, there's no metric really defined. And of course, that's exactly the situation. All these things are defined in terms of these null vectors, AI and BJ, all in the universal algebra of null vectors, which makes this possible, identification possible, which I think explains this relationship, the relationship between this and this equally well, this and this. It's all together.
Professor Garret, because in the first part of the line, you have a vector. In the second part of the line, you have an evaluate vector that is the expression that you need for a coordinate change. Then this part of the expression is related with a new representation of the same vector, partial xi.
Well, that's where it's not quite. That's not quite right as far as this is concerned. Whether the indices I is not equal to j, you can see this thing is 0 then. So I'm claiming that the fact that that's equal to 0 for I not equal to j, that's where the Finsler geometry arises from.
Then I am in the same state. I don't understand what is the meaning of this part. I was trying to.
Well, I'm probably not going to resolve this today, but I think I can define this. I will be able to next time. I'll define more exactly what I mean by the Finsler gradient. Well, you can see why Finsler geometry is confusing because, well, as Chern will say in this notices paper, no metric is really involved. Well, actually, a Minkowski metric is involved. And I think this whole confusion is exactly where this idea of a null vector comes in. It's a fundamental concept.
Dear Garret, you said that a Minkowski metric is involved in the background here.
Exactly.
Remember that my father, Professor Tolga Yarman, and his team, including you yourself, are very much engaged in bringing about the end results of general relativity and tying that up to quantum mechanical results. and special relativistic results. So the quantum theory of gravity proposed by my father and his team, and including yourself, depend on such a Minkowskian backdrop in order to set the local observer and the distant observer in a gravitational scenario. So this all ties together. So explain to us a bit more how you are introducing the Minkowski background as a prerequisite here.
Oh, well, the CIs are exactly the generators of the Minkowski Minkowski space-time, or the more general Clifford algebras G1n. So again, well, I have to go back up now. Okay, let's go down to okay, here it is. So we take n plus 1 null vectors, all having square 0. And we define the geometric algebra 1n by putting a Minkowski metric on it. Okay, so we define E1 equal to C1 plus C2, F1 equal to C1 minus C2, and then we have this very strange for Fk. Remember, that's generating the geometric algebra 1 comma n. E1 squared is equal to plus 1, F1 squared minus 1, F2 squared, all orthonormal vectors. They're all anti-commutative with each other. That's easy to show. I'm not showing it here. And I give examples here. Spectral basis type. So this is where that last slide, where the Minkowski metric arises, or the Lorentz metric arises. So I'm sorry your father, Dr. Toga Yarman, was not able to attend today as well. It's too bad he was.
This recording will be available for me to show later to him.
Yes, I think it is being recorded.
Yes.
Dr. Payton knows more about the details about that.
Yes, no problem.
Okay, so it will be available on the web then. So that's good. So I'm excited about this because I think that, like I say, I think that what I'm calling now null vector manifolds are equivalent to, that's my conjecture, equivalent to Finsler geometry. And it's well known that Finsler geometry involves both Riemannian geometry, which goes back to Riemann, and also Minkowski geometry or Lorentz geometry, which has signature 1 comma n, or if you like, n comma 1. So it's all related to the classifications of these geometric algebras. Standard classification only uses the idea of what I'm calling global duality, whereas the new duality, which is closely related to the matrix product as well, all represented in terms of complex or pairs of matrices or matrices of quaternions and so on. Very important, which is lost in the usual sense because they don't have the notion of a local duality. But look at Chern's work. That's why I'm excited about it. I think it's really equivalent. That's my conjecture, which I hope will attract attention to geometric algebra of arbitrary signature. I think that classification of geometric algebra can be equally done only in terms of this idea of local duality as well as global duality. Okay, well, anyway.
I'd like to watch your table about geometric algebras. I think that if you can put again this, because maybe some of the principal ideas of your document are presented here, and I think that it is nice to.
Okay, this is simple examples right here. One,
No,
two.
but your table, I think you put it before in one page, I remember.
Oh,
Here,
this table.
okay,
Oh,
here.
yeah.
I think this is important, but you are putting here some properties of the
Exactly.
sets that or algebras that you are using.
Yeah.
Then I think that from here we can take some of these principal ideas. For example, in the sale of local duality, I think it is clear here that you are changing the metric in this part because you are changing the orientation of the space in the right place. Yes, here in local duality. Then you are changing the properties of the transformation of the set that in one part you go to the anti-symmetric part and in the other to the symmetric part. Then after of this, you get the product of these two lines in the line that you put like G1n to a square. I think that this is an important relation. And the other one, I understand this, okay, but is related with here covariant and contravariant meaning are related with the base and complementary base of one
These Grossman algebras.
yes. Okay, you are saying that the A dual is equal to B. And then this is the complementary base of a set A, for example. And then we can work in this way with the properties of covariant and contravariant because you are transforming from one base to the complementary base. The first one is is generated by the null vectors, and the other one is generated by the complementary part that is the dual of the first. I think that these rows are presenting the general idea, and I think that we can take this like a wide to the work.
Okay, the interesting point I'll make here is that when you define, so this, you can think about this as being spaces. The simplest case, of course, is like you have a flat space, a flat, for example, what is a flat Finsler geometry? That's just spaces. It has no curvature. You don't need all the curvature. The curvature tensor arises, well, it's defined in Finsler geometry in terms of the Riemann curvature tensor, and all those things can be defined in terms of these. Well, starting out with my thesis, I was working with vector manifolds, and that was, of course, this side of the drawing. But maybe it should be, as I say, it should all be. It's all part of Finsler geometry, which I did not recognize at the time, which I only realized now in the last couple of weeks. So there's a lot of work to do to understand exactly but that's right. So I'm identifying covectors and contravariant vectors are as vector. Well, you saw as we identified them, but this really goes beyond that, and that's what's causing the confusion. In fact, even Chern recognizes it. Yeah, it's very confusing because there's too damn it. But that's right. If you look at flat spaces, no curvature involved. That's just that's the simplest possible manifold is just a flat space where the curvature is zero. It's just a vector space, basically. For example, Riemannian space is a flat space, Rn, okay? And well, actually, we put metrics on RPQ, okay? That's the way we look at these vector manifolds in terms of this global duality and local duality. But this seems to be not recognized, this idea of local duality, and I think it's important, both in Finsler geometry and in even in this, maybe that's the confusion. I haven't closely enough identified exactly what this side means when I say A star equal to B, and that's the confusion that Dr. Page is expressing too, as well as Dr. Cruz. But anyway, there's much more work to be done, especially, of course, we're interested in unifying general relativity with quantum mechanics. Well, that's this interesting paper
or in this case, recognizing that my father's work has merit in regards to his and his team's quantum theory of gravity
SWB audio capture
publication
not registered.
recently appearing in Annals of Physics, as you will remember, dear Garret.
Okay, well, maybe we can finally put these languages together in a unified way. That's an interesting.
Indeed.
So I'm looking forward to discussing that more, actually.
Very good.
Okay, well, we've come up on 2 hours since we started, so I think this is an appropriate place to end the meeting for today. Before we depart, we should just make some decision about the presentation in 3 weeks' time. Dr. Cruz, you just distributed a document this morning with on the subject of category theory and duality. Is this something that you would like to present in 3 weeks' time?
Yes, I like to present something around this this draft. Yes. Mm-hmm.
Yes. Okay, and Dr. Sobczyk, you said you may or may not have more comments in 3 weeks' time about Finsler geometry.
Maybe at the end of we try to put some of these ideas, develop a little bit more. But I will be in Mexico at that time, so my computer facilities won't be as good. But maybe I can still get a handle on it, and so 3 weeks' time I should be able to set things up, and be. That's a good time for me then, 2 and 3 weeks.
Okay, well, let's agree then that in 3 weeks' time, Dr. Cruz will be making a presentation on duality and category theory, and that you may have comments at that time about the relationship to Finsler geometry.
I will send
other
all
aspects of
these references immediately after the talking today, so you can have the talk slides and everything.
Okay, and this document that Dr. Cruz distributed this morning may not be available to everyone. Dr. Yarman, I'm not sure.
Yes, of course,
yes.
please send to.
I will write my email to the chat.
Okay, thanks. Okay.
Also, Professor Cruz, if you can send me the paper, I didn't receive it.
Okay. Of course.
So if you'll excuse me, I have to visit my father for a talk now. I enjoyed very much this conversation, and I am happy to meet you all. So thank you very much. Goodbye for now.
Okay.
Okay,
Bye.
yeah, I'll talk to you later.
Bye-bye, Garret. Bye.
I'm glad you could attend.
Bye.
I'm very- yeah, you really helped me out. I could, technically, I would have screwed it up.
Okay, bye now.